And it says we're live. Yeah, it says we're live.
All right, hello everyone. Welcome to our live session. I'm going to hand it over to Chris to welcome you all as well.
Yes, welcome to another live session, again from London, as we will be for the next few months, where it is currently the warmest February on record. So it's good news of coming to London from Arizona. Of course, the bad news is that's part of climate change. That's not good for anyone. And then the other bad news is next month is Brexit, and who knows what's going to happen then. So let's just take refuge in the large universe beyond these shores. Ready for your questions.
All right, then the first question from excuse me, one of our live viewers is there any evidence of white holes?
Not directly, and so just to back up to what a white hole is, it's a hypothetical object that really represents a sort of rift in space-time. It's sort of the counterpart of a black hole. So potentially and hypothetically, black holes could connect different regions of space-time where the loss of information in a black hole, which represents a place that you can't escape from, light can't escape, somehow connects to another region where the information can get out or light gets out. It's formally allowed in general relativity. You can conjure up a situation mathematically and in the gravity theory where that could take place. But that would require space-time to be quite complex and interesting and convoluted. And everything we know about the universe as a whole says that space-time is almost perfectly flat. The universe is flat, spatially flat. And the black holes that we know of are very small regions where space-time is pinched off by the intense gravity of a collapsed stellar remnant. But there's no indication that they would conceivably connect to a different part of space-time because the global curvature of space-time is so modest. So white holes probably don't exist. Ready for the next question.
All right, so that's great, and it leads us nicely into our next question, which is from one of our live viewers who asks, it's KCC or KKCC family, who asks, I'm hoping Professor Impey could explain what astronomers mean when they say the universe is flat. Could you help me understand the concept as well as its implications?
Sure. So when astronomers talk about the curvature of the universe, just in general, whatever curvature it has, they're talking about a concept that comes out of general relativity. In Newtonian gravity, in the gravity theory we had for hundreds of years, from Newton's time until the early 20th century, there was no such thing as the curvature of space. Space was linear and flat and obeyed the laws of Euclid's geometry in 3 dimensions. Simple as that. General relativity opens up the possibility of curved space-time because it is a geometric theory of gravity where there's a mathematical connection through complex equations, but conceptually it's simple, between the curvature of space-time and the amount of mass energy density in that region of space-time. So a black hole represents a place where the density of mass energy is so high that the space-time is enormously curved and essentially pinched off and lost to the rest of the universe. But there can be more modest versions of that curvature from larger distributions of matter. And so when you solve the equations of general relativity for the universe as a whole, the expanding universe, the general relativity theory explains the expansion of the universe and says that it could easily contract as well as expand in a different situation. That's in a situation where the space-time, the global space-time, the large universe, the universe as a whole, could have some curvature. And mathematically, that curvature can have 2 different signs. It could be negative curvature or positive curvature. It's hard to think of this kind of curvature in 3 dimensions because we're embedded in 3 dimensions. So we can't visualize something that's the same number of dimensions as the space we occupy. We can more easily imagine it in a 2-dimensional analog, and a positively curved 2-dimensional space is like the surface of a balloon or any large spherical or curved object. And the negative curvature of space-time is analogous to a saddle. The way to measure the curvature, either on those 2-dimension surfaces that I just talked about or in the 3 dimensions of our universe, is just to send light beams out. So if you imagine sending parallel light beams out from the Earth out into space through the universe, if space had a positive curvature, it would focus that light, and those light beams would eventually converge. If space had a negative curvature, those light beams would eventually diverge. And that's, of course, what happens to lines, parallel lines drawn on the surfaces of spheres. They converge, or saddles, they diverge. You can try it with a saddle shape if you don't believe that. So those are the curvatures of global space-time out of general relativity. And the transition between the positive and negative curvature is obviously zero curvature, which is flat space, as obeying Euclid's principles and rules in 3 dimensions. And so flat space is space that doesn't have any global curvature. The measurement of curvature of space-time has been done most precisely with a microwave background, because that lets us see radiation that's been traveling an enormous distance through the universe from just after the Big Bang till it reaches our radio telescopes. And so it gives us enormous leverage to see whether these photons, these microwave photons, are actually converging or diverging or not changing their directions at all. And the answer is they're not changing their directions at all. So microwave observations tell us within a few percent that there is no space curvature, which is maybe a little disappointing since space-time could be curved in general relativity, and it turns out it's not curved. Now that fact becomes very interesting in cosmology and led historically to the birth of the inflationary hypothesis, but that's a whole different matter. So I'll stop for now. Ready for the next question.
All right, thanks, Chris. The next question is from Alexander, who's on with us live, who asks, general relativity links mass and space curvature together. But the Higgs boson makes particles have mass. So should general relativity somehow be updated to ignore mass and use the Higgs boson in equations? What's the connection between those two, and how will it be resolved?
Okay, that's an interesting question. So yes, the Higgs mechanism, let's call it a mechanism rather than a particle. It is the carrier of the mass, essentially, of any particle. The Higgs mechanism is what gives the attribution of mass to things we call particles. And you can almost, rather than thinking of it as a force or a field, think of it as a sort of suffusing fluid through all space that has some viscosity. And so particles have more or less inertia traveling through this invisible fluid that has viscosity, and they therefore manifest more or less mass. And so that's the kind of conceptual idea of how Higgs mechanism gives particles their mass. So the Higgs mechanism is not formally connected to general relativity at all. The Higgs mechanism emerges out of the standard model of particle physics. And that model is based on quantum mechanics, which describes events on a very small scale. And it involves forces, the weak and strong nuclear force in particular, and electromagnetic force, if photons are involved, that are vastly more powerful than gravity. Gravity is by far the weakest force. So there's no formal connection between the Higgs mechanism or the Higgs boson and general relativity, because the Higgs mechanism operates at a completely different energy scale from gravity itself. People have been looking for a connection because that's the way we would unify all the 4 forces, and it would essentially require a quantized theory of gravity. A quantized theory of gravity would naturally make an association with the Higgs effect, the Higgs boson, the Higgs mechanism, and all the other fundamental particles. People have been looking hard for this theory, working hard on it, and not with very much success, actually. It's a very difficult thing to do. So at the moment, there's no connection, but people hope there might be, and they can find one, theoretically, and then prove it observationally subsequently. Ready for the next question?
Thanks, Chris. So the next question is, again, related to gravity, and you answered this a bit, but you can maybe focus more on how it works. But the question is, I've been reading about Einsteinian gravity, and I'm still wondering about the cause of gravity, and then also, what does quantum spin look like? So there's kind of 2 questions embedded there.
Well, quantum gravity, so Einstein's gravity and general relativity, is the formalism that relates the curvature of space-time to mass energy. It's also hyphenated. It's not just the mass density in a region of space. it's mass and energy. You combine the two. And since they're equivalent, you can convert mass into energy. That's very logical. That makes sense. That's another one of Einstein's insights. So you don't actually have to have any other attribution of matter. You just have to have a mechanism whereby the existence of mass and or energy curves the space that it occupies. And then all the results of gravity theory follow from that same simple assumption. And it is an assumption. And Einstein got there, of course, by noticing that two different ways of defining mass appeared to be identical. It's called the equivalence principle. It's the fact that experimentally in physics, before Einstein developed his theory, it seems, by very accurate measurement, that the inertial mass, the resistance of an object to any change of its motion caused by anything, any force, is the same as its gravitational mass, which is the mass that it exhibits moving in a gravitational field. And that coincidence, actually accurate to 1 part in 10 to the 15, or 1 part in 1,000 trillion, was too much of a coincidence for Einstein not to think it had a profound underlying explanation. And so his underlying explanation is the theory of general relativity. The second part of the question about spin particle, I can't remember the exact phrase of the question, though.
Basically, the question was, what does quantum spin look like?
Oh, well, quantum spin is just to be simple about it, it's not at all physical spin. So we have to remove that idea from our heads. It's natural to have a little picture of a spinning top or a spinning orb like the Earth, angular momentum, and so on. It's nothing like that at all. It's a very abstract quantity. So quantum spin is simply a quantum property of matter that has nothing to do with rotation or spinning particles, because it can, for example, be true of an electron. An electron has no extent in the standard model of particle physics, so there's not really a little spinning top at all, since it's a particle with no size. It's a quantum property which, depending on the nature of the particle, has integer or half-integer value, and those matter because the way particles interact and can interchange properties keep them separate if they have half-integer spins or full integer spins. So in this quantum property, if it has integer value, there are bosons, like a photon or other particles. And if it has half-integer spins, they're called fermions, named after Enrico Fermi, like an electron, for example. So it's a quantum property that is conserved in particle interactions and is a very fundamental property of all particles in the standard model, but it has nothing to do with spin or rotation. Ready for the next question?
All right, thank you very much. The next question is from Rock Kokalj, who asks, how can we amateur astronomers help? And I'm assuming he means the enterprise of professional astronomy. Is there even a place for us as the latest findings get very complex?
Absolutely. There's probably more of a place for amateur astronomers than ever before, for several reasons. The first reason, of course, is that the hardware and capability available to amateur astronomers is vastly superior to what it was 10 or 20 years ago. The bar is now low enough for amateur astronomers of fairly modest means and budgets to have a CCD camera at the back of their small telescope. And having a small CCD camera, it doesn't have to be cooled with liquid nitrogen the way the professional cameras are, but just with a thermoelectric cooler, will deliver, amazing images compared to the past, compared to photography or the naked eye, obviously. So small CCD cameras are really easily available, and you can get pretty good results with a modest-sized telescope. Also, the telescopes, are pretty sophisticated now. Most of them have drives. Most of them have go-to mechanisms, as they're called, that will just read from a computer list and point around the sky and move rapidly according to a preset list of positions. That takes away some of the romance and perhaps the raw skill of the amateur astronomer finding objects in the sky, but it makes observing much more efficient. And so there are amateur astronomers who have observing programs where their small telescopes with CCDs behind them are hopping around the sky, for example, observing 50 or 60 nearby galaxies in a night looking for supernovae. And then they go back and do it the next week or the next night and gather data over a long period of time. And that's one example of a niche where amateur astronomers make a huge contribution, because a supernova explosion in a galaxy is very rare, one per galaxy per century. So you basically have to be staring at a lot of galaxies very often to get lucky enough to see one supernova. So that's one area where amateurs make a huge impact. Another, of course, is exoplanets. The precision of the CCD allows you to measure transits, and some nearby stars and nearby exoplanets are bright enough you don't need a big telescope to do it. Remember, the first exoplanet in 1995 was discovered with a 1-meter telescope. That's fairly big, but amateur astronomers actually do have those telescope sizes now. So those are just two areas, exoplanets and supernovae, very important areas of astronomy. Research is very important and active in those areas where amateurs can contribute. There are 50 or 55 types of variable stars, and the astrophysics of the variability mechanism in stars is not still fully understood, and more data is needed. So amateur astronomers observing variable stars are making big contributions too. And then, of course, because amateurs have a lot of time on their hands, many of them are retired and it's their passion, so they're spending a lot of time out with the sky, much more than a professional astronomer who may get a week or 10 days of time on a big telescope per year. Amateurs are likely to see things that professionals won't see. Solar system objects is another area where they can contribute because some of those are quite bright when they get close to the Earth. So really it is a wonderful time for amateur astronomers to cooperate with professional astronomers, and there are many means on the internet and places where those collaborations and those data sharing arrangements can be set up and facilitated. Ready for the next question.
All right, thank you. And then I also want to mention that Laura, who is on with us live, had a similar question. So Laura, I think your question was answered in that response. Can you talk quickly, Chris, about any of those online resources that you know of where amateurs can get involved and places where they can go to get more involved in astronomy?
Yeah, the classic organization, because it goes back over 100 years, I think, is the AAVSO, the American Amateur Astronomer Variable Star Organization. So that's very classic research that amateur astronomers have done. So their website and mailing lists and forums are very useful. There's another whole realm of ways astronomers can participate in citizen science, but that wasn't the intent of the question, because citizen scientists don't typically need a telescope to do what they do. They're using professional data sets and learning things from those. For exoplanets, I don't have, unfortunately, off the top of my head where you would go. But I think actually Harvard Observatory is one of the main clearinghouses for work with amateurs on exoplanets. They have very active exoplanet research there. So I'd check out the Harvard Observatory website, and probably there's a place there. Ready for the next question.
All right, so now we will take a specific question from Laura, who's on with us live, who asks, can we determine the speed at which Andromeda is moving towards the Milky Way using Andromeda's blue shift? And if so, how? And if not, what could be done to calculate it?
Yes, the radial velocity, or the component of Andromeda's three-dimensional motion in space that is directly towards or away from us, is measured fairly simply by the Doppler effect. So it's a bright galaxy, of course, too. So this is not actually a very difficult measurement. And I don't remember the precise number, but it's roughly 100 kilometers per second. So the radial velocity was first measured decades ago, and actually better data doesn't really get you more precision because it's known about as well as we can know it. What has become added to that is, remember that radial velocity is just one component of a three-dimensional motion, so it's just a component of a vector, if you like. What has come in the last few decades with very painstaking work with the Hubble Space Telescope is a measurement of the transverse motion of Andromeda relative to the Milky Way. That is, its shift on the plane of the sky relative to distant objects, sideways. And that gives you the transverse motion. That's a very difficult measurement because it's very subtle, and it's not slow in real terms, but it's slow because of the great distance of that object. That's been measured now, and the combination of those two measurements, the transverse velocity and the radial velocity, give you a much better sense of the true space motion of Andromeda. And that's actually led to a revision just within the last 6 months. There was a paper actually only a couple of months ago with revised simulations of when Andromeda and the Milky Way would collide, and the timescales actually pushed off a bit. Some people were saying about 3 billion years from now. It seems to be more like 4 billion years. It's more of a glancing collision than a direct collision. However, the end result will be the same thing. The two nuclei will merge, will settle down and merge. The two combined galaxies will eventually settle down and form one enormous stellar system. Ready for the next question.
All right, thank you, Chris. The next question, excuse me, is from a live viewer. So Kushal is joining us again, and he always has the greatest questions. A lot of them are very technical, so we don't always have a time to get to the very specific ones, but we'll throw this one out there. Kushal asks, what causes variability in FU Orionis stars?
It's pretty much, it's in the same class. I'm going to, give the general explanation because it's most useful to most of the listeners. These are almost all the variable stars are evolved stars. They're stars that have gone past the main sequence. That is, they've ended their hydrogen fusing lives, as the sun will do in about 4 or 5 billion years, and move into shorter and more unstable fusion stages of energy production. And these instabilities, like when a new nuclear fuel kicks in, or when the star ejects an envelope of gas, as the sun will do as a red giant, for example, lead to the larger potential for instabilities. And an instability in a star, because the star is sort of thermostatically controlled as a fusion object, leads to an oscillation. So when you have an instability in a situation where there's negative feedback and it's regulated, you're going to get essentially an oscillation. And that's going to lead to a variability cycle in the light, because as the star condenses a little, it heats up, emits more energy, gets brighter, and that increased energy production creates pressure inside, which pushes the gas out, which cools it, reduces the energy output, and the light dims. And so you see a cycle set up that way. And it will only continue, it won't continue forever, it'll only continue for as long as the star is in that unstable stage. So an FU Orionis star is just in one of these few dozen categories of variable evolved star. The prototype was a star. The way astronomers name stars, Orionis means it's in the Orion constellation. FU means it's part of a catalog where people were basically numbering, or rather lettering, stars and then moving through the alphabet of the second letter after they got the first 26. So you can sort of do the math on how many stars were in that catalog. They're interesting stars because they tell us about how stars work. Each one is a little astrophysics experiment. And so we can learn something from the nearby bright examples by studying them carefully. Ready for the next question?
Excellent. The next question is from Kieran, who is on with us live. Kieran K asks, can you share your thoughts on the WOW signal?
Yeah, the WOW signal is an iconic, sort of famous episode in the history of SETI, or the Search for Extraterrestrial Intelligence. It was, now I'm not going to, my memory isn't good enough to get the year, but I think it was the early 70s. It might be 1974. It was when radio astronomers were listening for signals from stars that could represent an alien civilization emitting radio waves in our direction. And they were obviously listening for radio signals that were that had to be artificial. And what does that mean? Well, radio signals come from space for all sorts of reasons. When electrons spiral in magnetic fields, they emit radio waves. That's cyclotron or synchrotron radiation. That's pretty standard stuff. When plasmas interact with radiation, you have Bremsstrahlung radiation. So there are physics mechanisms to give radio emission. They have nothing to do with extraterrestrial civilizations. But if you see a signal that's extremely narrow bandwidth, so very rapid or spiky in time, and especially one that repeats, that doesn't have a normal physical explanation like those other physics mechanisms I just talked about. So that's the kind of thing people were looking for. Frank Drake started this work in 1959 with the project OSMA, where he looked at two very bright stars, Green Bank radio telescope. The wow signal happened in Ohio, at Ohio State. Ohio State had a dipole array telescope. I think it was built in a football field that had been repurposed for this reason in the 1970s. Ohio State has had a long tradition of radio astronomy. And so someone was sitting at the control of this radio telescope. Now, back in those days, early 70s, really before serious computers, laptops, and some forms of digital technology. So they were using an old-fashioned strip chart, where the signal at the back end of the radio telescope was just coming out as a squiggly pen on graph paper, and the graph paper just feeds out and you see the signal over time. And in the middle of the night, I don't remember the date or anything, suddenly in what would just a noisy trace, just a squiggle that's just radio noise or hiss, there was a great spike. It leapt almost to the edge of the chart. And the person looking at that was amazed and impressed enough, because it was such a strong signal. It was so narrow, again, indicating a not obvious explanation astrophysically, that he wrote "wow" with exclamations next to it on the strip chart. And of course, knowing where the telescope was pointed at that time, they went back and looked in that same spot night after night and never saw anything else. I think they went back not only days later, but weeks and months later, and never saw a recurrence of that signal. So it's one of those very disappointing, exciting but disappointing episodes in SETI, where someone saw a one-off signal that looked artificial on its face, that didn't have any other obvious cause. It wasn't radio interference. It didn't seem to be caused by a terrestrial phenomena. But if you never see it repeat, you simply can't attribute it to alien civilizations. That's too radical a hypothesis. So the wow signal is just, in the annals of SETI, is just one of those slightly frustrating episodes where people thought they were onto something, but it didn't pan out. Ready for the next question?
All right, thank you very much, Chris. The next question is from Robert Baker, who asks, who's on live with us, and asks, how is machine learning used in astronomy, and then is specifically interested in applications for exoplanet searches?
Yeah, I'm seeing a lot of papers now about AI and machine learning. It's a boom area in astronomy. So the two areas where machine learning is proving particularly powerful are, as the questioner, as Robert asked, in the area of exoplanets. Basically, the trace is, if you're talking about, it's particularly looking for the eclipse signatures of transiting exoplanets. I mean, the eclipse profiles can be quite noisy and difficult to pick out of noise, and the eclipse profile itself can have different shapes, because in some situations, the shape of the transit profile, when the light dims as the planet crosses the face of the star, it can have different shapes if the planet rather has an atmosphere, thick atmosphere. It can be less steep-sided, for example. So it's quite subtle to find these signatures. And so machine learning has been applied to try and train the machine, obviously the neural net or whatever mechanism is being used, on archetypal forms of transits where you're very sure it's a transit because you've seen it repeat over and over again, and where there's not much noise in the data. And then unleash the neural net or the machine learning algorithm on data where you don't know what's in the data, and you're trying to get it to recognize very weak and difficult to detect transits. And it's work that, of course, you could never do by eye. So you need a machine to do this. And you don't know where the planets are going to be, and you don't know how many of them there are going to be. So again, you have no real clear expectation. Again, a good situation for machine learning. The other area where machine learning is making a really big contribution is in the detection and classification of faint galaxies. So when you take a deep image of the sky with a CCD, you don't see the classic archetypal, beautifully etched spirals like Andromeda or a nearby galaxy with all the star formation regions and spiral arms. You're seeing faint fuzzy blobs. And those faint fuzzy blobs may be symmetric or asymmetric. They may have blobs on top of them, which represent H2 regions or nuclei or supernovae or all sorts of things. And you're in the situation where there's a lot of noise, because these are faint enough, they're fading into the sky, and there's noisy data. And neural nets, again, can be trained to recognize galaxies. You can train neural nets or the machine learning methods on standard spiral and elliptical galaxies or irregular galaxies, or to look for supernovae, which are just a blob on top of a galaxy where a star has died and become almost as bright as the galaxy. And then again, in a way that couldn't possibly be done efficiently by eye or by hand or by astronomers staring at images, you unleash the machine learning algorithm on hundreds of thousands or even millions of images, hoping to pick out those rare cases of something interesting happening. You're not really using the machine learning. You can use the machine learning, of course, just to classify the galaxies as the different spiral types and elliptical types. That's very effective. That worked right away. But probably a more interesting use is to pick out exotic phenomena like nuclear activity or supernovae or galaxy types that hadn't been seen before. And that works very well too. Ready for the next question?
All right, our next question is from Kushal, who asks, how can black holes generate magnetic fields?
Well, the black holes don't generate the magnetic field. The magnetic field already existed. So if you think of the sun, which has a magnetic field, obviously, a magnetic field that winds up with a dynamo mechanism, becomes chaotic and then reforms, and that gives us the solar cycle. The magnetic field is entrained by the plasma, the sun's plasma. And because the star differentially rotates faster at the equator than the poles, that's what twists up the field and leads to it dissolving and reforming. But if a star collapses because of the lack of pressure support from the end of the fusion, then that plasma is suddenly compressed, hugely compressed. And since the magnetic field is entrained in the plasma, I mean, it's essentially trapped in the plasma because that's where the electrons and the protons are. That's where the mechanism for sustaining a magnetic field is. Then that magnetic field is pinched. You can just imagine the field lines being pinched or compressed or grabbed and squeezed, and so you get a much stronger magnetic field. And so the collapse of a star simply increases the strength of the magnetic field in proportion to the cross-sectional area of the star, so very rapidly when the star collapses. Of course, in the extreme version of a massive star dying, you can have a pulsar forming, a neutron star. And neutron stars can have magnetic fields that are up to about, I think the record is something like 10 to the 15 Gauss. That's incredible. That's 1,000 trillion Gauss. Black holes, in principle, have magnetic fields too, because, of course, they form from collapsed cores of stars, which originally had magnetic fields. But the magnetic field of a black hole, which is to say, within the event horizon, is not something we can measure. It's not observable. So it's just inferred and very likely that the magnetic field does exist inside a black hole. And because it was trapped in the formation of that object, it's not something we can measure directly, however. Ready for the next question?
All right, our next question is from Akanksha, who asks, Uranus rotates on its axis with a tilt of 98 degrees, and its rings and satellites also revolve around the planet vertically in the plane of our solar system. Wouldn't it mean that the orientation of space-time around the planet has been altered?
It could mean that, but there's a simpler explanation. It's a simpler explanation that we can't actually prove. So when we look at the solar system, we're just stuck with the way it is. It formed 4.5 billion years ago, and there was some rearrangement of the planets, including Uranus, a few 100 million years after the formation. But all the incidents, all the episodes of kind of violent formation and early activity that led the planets to be the way they are have happened in the distant past, over 4 billion years ago. So the simple truth is we'll never be completely sure. But what we think happened is that in the early solar system, when there were large objects flying around, not just the objects that would eventually form 8 significant sized planets, but other planetesimals that were Mars-sized or even Earth-sized, collisions with those objects could cause chaos and alteration of planetary properties. And so the best hypothesis is that Uranus, early in its history, was subject to a really big collision, like the collision with a Mars-sized object on the early Earth that led to the formation of the moon, and may have had something to do with the Earth's axial tilt being not zero. Remember, Mars has a very small axial tilt, and Venus too. So the Earth has a significant axial tilt. Sorry, Mars has a significant axial tilt. Venus is small, and it's our twin. So Uranus was knocked on its side, essentially. It has an axial tilt. It's not exactly 90. It's, I think, 87 degrees. And that's the best hypothesis of what happened. More interesting even is Venus, which, as I said, has no axial tilt, and that's because it's tilted completely by 180 degrees, and it counter-rotates. So it spins in the opposite direction of all the other planets as it goes around the sun. That makes no sense in the standard formation mechanism of the solar system. So again, as with Uranus, it's hypothesized that Venus was subject to a collision that just knocked it right on its head, inverted it at 180 degrees. And when a planet is knocked from its spin position to another orientation and subsequently forms ring systems or moon systems, because the collision happened very early, then those ring and moon systems will form in the orbital plane of its spin. And so naturally, the rings of Uranus are also tilted at 90 degrees, and its moon system as well. Ready for the next question?
Okay, our next question is from Peter, who's on with us live, who asks, why are the rocky planets near the sun while the less dense planets are further away?
It's a good question that people asked, early on in their investigation of the solar system. There seems to be a pattern in the solar system of this segregation, really, of two groups of objects. There's the inner planets, the terrestrial planets as they're called, which includes us. So it's Mercury, Venus, Earth, and Mars. And then there's a set of outer planets much further away from the sun, Jupiter, Saturn, Uranus, and Neptune. And they are much more massive, and they seem to be made of hydrogen and helium. Now that dramatic difference diminishes when we learn, as we did over a period of a few decades, that the gas giant planets also have rocky cores. They can't be directly observed because their atmospheres are completely opaque, very thick, can't see through them. But magnetometer readings from the orbiters, from the spacecraft that went to these giant planets during the 70s and 80s, have shown really beyond any doubt that there are rocky cores in each of the giant planets. They're not very well measured, their mass, but basically the best guess is that there are rocky cores that are 3 to 10 Earth masses in all the gas giants. And so that diminishes the difference, the dramatic difference between the two sets of objects, because there are large super Earth type cores in the big giant planets out there, and then they have this additional component of a gaseous envelope. So in the formation scenario, you now have a more unified idea where the planets, the rocky ones and the rocky cores of the outer ones, formed in the sort of same way by accretion, by gathering of material in the protostellar disk in the first really short time, 50 million years after the formation itself of the sun and the disk collapsing. And then over another period of time after that, the outer planets gathered gaseous cool envelopes of hydrogen and helium, the dominant gases in the solar nebula. Now, why didn't the planets in the inner part of the solar system end with those big gaseous envelopes? Two reasons. First is that they're on smaller, closer orbits to the sun, and so their zones, the zones they would have been able to sweep out or gather material, are much smaller, less material for them to gather in those inner radii. The larger planets were able to gather more material. And second, it's cooler out in the outer part of the solar system, further from the young sun in particular was more luminous than the sun now. And so the young sun would blast off material from the inner planets early on, especially early on when the sun was very active, whereas the solar radiation would not be sufficient to ablate or blow off the atmospheres of the gas giants. And those atmospheres just got to gradually accrete, and then it would accelerate as the envelope got heavier. It would pull in more gas and then more gas until the gas was all used up. And so you end up with gas giants and then small rocky planets. Ready for the next question?
All right. So we have live viewer Omri, who asks, I guess there's been a news story recently about physicists wanting to expand the LHC, the Large Hadron Collider. And the viewer asks, what do you think about building the next Large Hadron Collider? Is it necessary, and what would we learn?
Yeah, it's an impressive proposal. I downloaded the proposal from CERN last week, I think. I've seen the preliminary design proposal. So, the Large Hadron Collider was built into a pre-existing tunnel. I mean, it's a new collider at a much higher energy, but building these tunnels, 26 kilometers diameter, I think is the CERN tunnel that the LHC is in, is enormously expensive, and so you don't do it lightly. And so they've already taken the original CERN tunnel of that size and retrofitted it with stronger magnets and different detectors over a period of several decades. But at some point, they're reaching the end of the line. The superconducting magnets that CERN uses are as powerful as we think we know how to make them. And so the only way you can get higher energies is by having a bigger accelerator and more space for even bigger magnets. So there's no dramatic or wonderful new technology in play here. It's just scaling up this huge physics experiment to an even larger size, larger diameter. I can't remember how much larger. I think it's a factor of 3 larger diameter, and it's aiming to be close to an order of magnitude or a factor of 10 more energy in the highest energy collision. So why would you do that? The price tag for this is enormous. It's tens of billions of euros. I've read numbers like 50 or 60 billion euros when all is said and done and it's constructed. It would take a decade to build this thing. They want to start soon. Well, first of all, you want to do it because you've reached the end of the line with your current technology. And the other reason you want to do it is a slightly frustrating or negative reason, which is that the LHC in its current incarnation, it will only get one more energy boost before it's tapped out, has been rather disappointing. I mean, I'm a fan of high energy physics, and the Higgs discovery was amazing, but there's been no other major discovery. There's been some very interesting detailed physics found, not all of which is fully understood, and some of which may be very important. But there's no, front page headline discovery out of CERN since the Higgs. And that was 5 years ago now. And what they hope for, of course, is supersymmetry. They hope to detect the particles that are the counterparts in the supersymmetry theory that unifies 3 of the 4 forces of nature. Every fermion has a counterpart. Every boson has a counterpart. There are a set of shadow particles that unite the integer and half-integer spin particles. And one of those stable supersymmetric particles could be the dark matter. That's the big lure of supersymmetry. But it's also a lure because if that theory is correct, then we're moving closer to a fundamental theory of matter and nature. And it would take another accelerator to do that. There's signs that CERN itself will not find a supersymmetric signature. In fact, it's actually ruled out a number of the originally favored supersymmetric theories. There's many variations of the theory, so it hasn't killed the theory dead, but it's, I would say, gravely injured the theory. And that has led to some pushback, of course, by people who are not high energy physicists, who have their own experiments to do and their own things they want to spend money on, because they say, well, what if you don't find anything? Is it really worth building a huge, incredibly expensive accelerator when you're already not finding the thing you thought you'd find with the LHC, and you're going to put a bunch more money in? Well, that's the trouble with science. You don't know where you're going to go. You don't know where the discovery is going to come. It's an act of faith at some level to keep going to understand the theory of nature. So they're making their case right now, and we'll see how successful it is. Ready for the next question.
So a follow-up to that question is, do you think that the standard model of particle physics will ever be proven wrong?
It's possible. There are physicists who are uneasy, very uneasy about the standard model of particle physics. The discovery of the Higgs mechanism and the detection of the Higgs boson 5 years ago was the crowning achievement of the standard model. It was the last missing piece, if you like, of the standard model. But even as the standard model had its sort of final, crown put on top of it, the piece that was anticipated and finally detected by the Large Hadron Collider, the Standard Model is known to be incomplete. It's an imperfect description of nature. Because although the Higgs mechanism says what the mechanism to give particles mass is, it says nothing about why the masses are the way they are. Why is a proton 2,000 times more massive than an electron? Why are there 3 tiers of quarks of different masses? The muon, the electron, the muon, the tau particle, and so on, the 3 generations of particles. These families of particles are not explained by the Standard Model. Also, dark matter, of course, is not explained, and that's going to have to come out of supersymmetry, which is an extension of the Standard Model. It's a speculative theory. And then finally, gravity is not part of the picture here. And so the Standard Model of particle physics eventually, at some level, is going to have to say something about gravity. Because in the Standard Model, there's a particle called a graviton that has a spin of 2 in this sort of abstract spin quantity particle physicists talk about. And so the Standard Model of particle physics, imputes a graviton, and no one's ever observed a graviton. No one's ever shown that gravity travels with this particle called a graviton traveling at the speed of light. Those are experiments that have never succeeded. So how do you put gravity into this picture? And it's possible, and some physicists, some quite reputable ones, think that maybe the whole thing is on the wrong track, that it's more fundamentally flawed than we imagine. So physicists argue about this right now, and it's a sort of unstable situation, I'd say, at the moment, which is interesting, because it's not sterile. It's not like the science is going nowhere. It's going to go somewhere interesting, probably in the next decade. Ready for the next question?
All right, so the last question that we have time for today comes from Chris, who asks, is it practical for amateur astronomers to do spectroscopy? What could be contributed with a small spectrograph and a moderate-sized telescope?
It is now, for reasons that I mentioned in the earlier question about what amateur astronomers can do, the power of amateur astronomy equipment is such that spectroscopy is now on the table. Now, as soon as you get into doing spectroscopy, however, you're kind of pushing it, because you're taking, the light that you might have put into an image and you're dispersing it in wavelength. And that means that light will be arrayed as wavelengths or colors on the CCD. And that means its contrast relative to the sky background or the noise of your detector is less. So spectroscopy is definitely more challenging than imaging or photometry. And I would think that you need a telescope in the realm of, good fraction of a meter-sized telescope and a decent CCD to do spectroscopy that was meaningful on objects that were faint enough to be interesting. So it's a bit of a niche, and I would say only high-end equipment in size and throughput and the quality of the CCD can really do spectroscopy. Also, you need a spectrograph on your telescope, and you need one with high throughput. It must be very efficient in its use of light, otherwise the whole thing gets hard again. And spectrographs are not cheap. So because the gratings they use, holographic gratings typically now, are beautifully accurate, but they're not cheap at all. So it's a pretty high-end capability. I would say it's useful. I actually think that it's scientifically easier for an amateur astronomer to make an impact with imaging or photometry, and especially synoptic observations, which means observing something over and over again with a particular pattern, because that's a niche that professional astronomers can't really do. Just as a reference point on this conversation, the major telescopes of the world, the big ones, the 4, 5, 8, 10-meter telescopes of the world, something like 2/3 of their time is given over to spectroscopy, if they're optical telescopes. So spectroscopy is really the prime mode of most of the world's largest telescopes, with photometry or imaging, wide field imaging being the rest. So professional astronomers have sort of pushed spectroscopy to the limit, which makes slightly less real estate for amateurs to contribute with. That's been a great set of questions. Thanks very much for your attention, and we'll be back with you in a couple of weeks. Thanks to all our help we had getting this session going.
Excellent. Thank you very much, Chris. So back here in the office, it's me, Matthew Winger. We have Alexander Danahy, who has been doing all of our tech support, getting the live session running, and Victoria Pereira, who has been grabbing all of your questions and making sure that we can keep track of everything that's been asked. So thanks again, Chris, and we will see everybody next month when we do another one of our live sessions.